Welcome, everyone. I'm excited to kick off this course on mobile systems security. Today, we're starting with Lecture 1, Introduction. On this first slide, you'll see the course code ITCR 613 and the title Mobile Systems Security. We'll be exploring the fundamentals of securing mobile systems, the unique challenges they present, and the key concepts you'll need to understand throughout this course. So, let's get started and look forward to a great learning experience together. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a look at some of the top issues facing mobile devices today. First, physical security is a big concern. Things like theft or loss can expose sensitive data. Secure data storage on disk is also critical. If someone gains access to the device, they shouldn't be able to easily read stored information. Strong authentication methods are essential, but the challenge is that many mobile devices have poor keyboards, making complex authentication more difficult. Supporting multiple users securely on a single device adds another layer of complexity, especially when it comes to safeguarding each user's data. Creating a safe browsing environment involves protecting users from malicious sites and content. Operating systems need to be secure themselves, providing a solid foundation for all these safeguards. Application isolation is key here. It prevents malicious apps from affecting others or accessing data they shouldn't. Information disclosure remains a significant threat, with malware such as viruses, worms, trojans, spyware, and other malicious software constantly evolving. One of the ongoing challenges is the patching and updating process, which can be difficult to execute promptly on mobile devices, leaving vulnerabilities open longer than they should be. Secure communication protocols like SSL are vital, and strict enforcement of their use helps protect data in transit. Phishing attacks continue to be a major threat, tricking users into revealing sensitive information. Cross-site request forgery, or CSRF, exploits trust between a user and a site, making it another security concern. Location privacy and security are increasingly important as mobile devices track our movements, raising concerns about who has access to this data. Insecure device drivers can introduce vulnerabilities that hackers might exploit, so ensuring their security is crucial. Lastly, multi-factor authentication adds an extra layer of security, making it harder for attackers to gain access even if one factor is compromised. Overall, these issues highlight the importance of designing mobile device security with multiple layers, addressing both technical and user-related vulnerabilities to keep our information safe. Let's take a closer look at some of the top issues facing mobile devices today. First, physical security has always been a bit of a weak spot. Devices are easy to lose or have stolen, which can lead to serious information leaks. Plus, there's the risk of unauthorized usage, such as when someone borrows a device and gains access without permission. It's important to recognize that traditional physical security measures often haven't been enough to prevent these problems. Moving on, another critical concern is secure data storage on disks. Sensitive information like passwords, tokens, or other private data is stored locally on the device. While it's necessary to keep this data accessible for apps that need it, we also need to prevent unauthorized access. The goal is to strike a balance, making sure that only certain applications can access this data on an as-needed basis, while keeping it protected from potential threats. Overall, these issues highlight the importance of implementing strong security measures, both physically and digitally, to protect vital information on mobile devices. Let's take a closer look at some of the top issues facing mobile devices today. First, we have strong authentication paired with poor keyword options. While it's essential to have complex passwords or passphrases that include a mix of letters, numbers, special characters, and even spaces, implementing this on a mobile keyboard can be quite challenging. The standard mobile keyboard isn't always designed to easily support such complex inputs, making it difficult, if not impossible, to create truly strong passwords. Moving on, another significant challenge is supporting multiple users securely. Unlike traditional computers, mobile devices typically don't have a way to log in as different users with separate environments. This means there's no straightforward way to differentiate between personal and business use in terms of application access. Because of this, a one-size-fits-all security model doesn't work well. Instead, we need a tailored security approach for each application to prevent data exposure, especially as these devices often contain both sensitive work information and personal data. Connecting these points to the overall theme, it's clear that securing mobile devices requires addressing these unique challenges, both in authentication and multi-user support, to ensure data remains protected in our increasingly mobile world. Let's take a closer look at some of the top issues facing mobile devices today. First, when it comes to safe browsing environments, the limited real estate on mobile screens makes it easier for phishing attempts to succeed. Since the URL space is small or sometimes hidden, users can find it harder to verify legitimate sites, increasing the risk of falling for scams. Additionally, the inability to view the full URL or even see it at all can leave users vulnerable to malicious links. Speaking of links, they're followed much more frequently on mobile devices. This convenience means users are more likely to click on links without fully scrutinizing them, which again heightens security risks. Now, shifting to secure operating systems, while securing an OS is no small feat, it's something all mobile vendors should prioritize. A robust security system isn't just about preventing data breaches. It also helps avoid system downtime and keeps the user experience smooth and reliable. Data loss, system crashes, and performance issues all undermine user trust and can have serious repercussions. So, in summary, these issues highlight the importance of strong security measures and user awareness to protect mobile devices and keep our digital environment safe. Let's talk about some of the top issues facing mobile devices today. First, application isolation. It's very common to see a variety of applications on a mobile device, whether they're corporate apps, gaming, or social media. The key point here is that being able to isolate these applications and the data they require is absolutely critical. It helps prevent one app from accessing sensitive information from another, which is essential for security and privacy. Now, moving on to information disclosure. The data stored on a device, whether it's a desktop, laptop, server, or mobile, is often more valuable than the device itself. But with mobile devices, there's a higher risk because they are more likely to be lost or stolen. This makes protecting that data even more important. Additionally, when mobile devices access other networks, like through a VPN, there are additional concerns. If authentication mechanisms aren't strong enough, unauthorized access can become a serious vulnerability. So, ensuring robust authentication is crucial to safeguard sensitive information. Overall, these issues highlight the importance of implementing effective application isolation and strong data protection measures, especially given the unique risks mobile devices face today. Now, let's take a closer look at some of the top issues facing mobile devices today. One of the biggest concerns is security threats like viruses, worms, trojans, spyware, and malware. Just like with desktop computers, mobile devices are vulnerable to these kinds of attacks, but they also bring new challenges due to their unique environment. It's important to learn from what we've seen on desktops, but we also need to adapt to the mobile world and the different types of attacks that come with it. Another significant issue is the patching and updating process. While technically updating software might seem straightforward, in practice, it's quite complex for mobile devices. Carriers, for example, face big hurdles when it comes to deploying immediate system updates. There's often limited response time for testing, which makes quick updates difficult. Additionally, effective patching requires close coordination among several parties: the operating system developers, the carriers, and the handset vendors. All of these groups need to work together seamlessly to ensure that security updates are delivered efficiently, which is no small feat. So overall, these issues highlight the importance of ongoing vigilance and collaboration in maintaining mobile device security. Let's take a look at some of the top issues facing mobile devices today. First, there's the challenge around the use and enforcement of SSL. Older devices often lack the processing power to properly enforce SSL without impacting user experience. In some cases, they even allowed for backwards compatibility, which can introduce security gaps. Meanwhile, some organizations still default to clear text protocols, mistakenly believing that the increased difficulty of sniffing data on 3G networks makes this acceptable. But this assumption can be risky, since data can still be intercepted. Another issue is the abundance of transitive networks between the mobile device and the end system. These multiple layers can create additional points of vulnerability, making it harder to ensure data security end-to-end. Now, shifting to phishing, users on mobile devices tend to be more prone to clicking on links without considering safety. This is often because mobile screens have limited real estate, making it difficult to display the full URL or necessary security indicators. As a result, users might not recognize malicious sites, increasing the risk of successful phishing attacks. All of these points highlight the complex security landscape mobile devices face today, emphasizing the need for better safeguards and awareness. Let's take a look at some of the top issues facing mobile devices today. First up is cross-site request forgery, or CSRF. This is a particularly big problem for mobile HTML sites that haven't implemented proper protections, because mobile users often find it easier to click on links, especially on smaller screens or through email. Attackers can exploit this tendency. If a site is vulnerable, an attacker can trick a user into unknowingly performing actions like updating their address, email, or password on that site. It's a serious security concern that highlights the importance of safeguarding our mobile web applications. Moving on to location privacy and security, many mobile users have long believed that once they carry a device, their location privacy is compromised. And in many ways, that's true. Users often willingly share their location data through apps like Google Latitude, Foursquare, and others. While these services offer convenience and personalized experiences, they also pose risks if this data falls into the wrong hands or is misused. It's a reminder that, as users, we need to be aware of what information we're sharing and how it can impact our privacy. These issues connect directly to the broader theme of mobile security, balancing usability with protecting user data. Now, let's take a look at some of the top issues facing mobile devices today. First up, insecure device drivers. Typically, most applications shouldn't have direct access to system-level functions on a mobile device, but device drivers often do. This creates a potential security gap because if third-party drivers aren't properly secured, they could be exploited by attackers to bypass protections. Essentially, these drivers might provide methods for malicious actors to get around security schemes if they contain insecure code. Next, let's talk about multi-factor authentication. In the mobile world, many web applications rely on what's called soft multi-factor authentication. This usually involves verifying the user based on something like the browser, IP address, or HTTP headers. While helpful, these methods are quite vulnerable to spoofing because they rely on easily manipulated signals. To improve security, developers often create a device signature by combining various HTTP headers and connection properties. But even with these measures, this approach still falls short compared to native mobile applications. Native apps can leverage more secure, hardware-based authentication methods, making them inherently more resistant to spoofing and impersonation. So, understanding these issues, driver security and multi-factor authentication vulnerabilities, is crucial as we look to strengthen mobile device security overall. These challenges highlight the importance of designing robust, layered security strategies to protect users and data in an increasingly mobile world. Let's go through some essential tips for developing secure mobile applications. First, leveraging TLS or SSL is crucial because it encrypts data in transit, ensuring that sensitive information isn't exposed to eavesdroppers. Next, following secure programming practices helps us avoid common vulnerabilities and write code that's resilient against attacks. Validating input is also key. This prevents malicious data from causing harm or gaining unauthorized access. It's important to leverage the permissions model used by the operating system. Understanding and properly implementing this model helps us control what resources our app can access. Speaking of access, using the least privilege model means granting only the permissions necessary for the app to function, which minimizes potential damage if something goes wrong. Storing sensitive information properly is another vital step, using secure storage options rather than plain text or insecure locations. Signing the application's code adds a layer of trust and integrity, confirming that the code hasn't been tampered with. Establishing a secure and strong update process ensures that users receive patches promptly and that updates are authentic. Understanding the security strengths and limitations of mobile browsers is also important, especially since many apps rely on web content. Zeroing out non-threats involves clearing out unnecessary data and permissions that could be exploited. Lastly, designing URLs that are secure and intuitive helps users trust your app and prevents phishing or man-in-the-middle attacks. All these tips tie together to create a comprehensive approach to developing mobile apps that are not only functional, but also resilient against threats. Let's dive into some practical tips for secure mobile application development. First up, leveraging TLS or SSL is crucial. Make sure to turn on Transport Layer Security or Secure Sockets Layer by default. This helps protect data as it travels between the app and the server. It's important to enable both confidentiality, which keeps data secret, and integrity, which ensures data isn't tampered with. Often, environments focus on confidentiality, but forget about integrity, so double-check that both protections are enforced. Next, following secure programming practices is vital. I know there's often a rush, especially when deadlines are tight and budgets are small, pushing developers to ship quickly. But rushing can lead to skipping important security checks. Thankfully, we have a wealth of security frameworks and coding guidelines available. Use them. They can help you write safer, more resilient code, ultimately making your app more secure and trustworthy. Remember, investing a little time in security upfront pays off in the long run. Let's talk about some important tips for developing secure mobile applications. First up is validating input. This is crucial for both native apps and mobile web applications. Since mobile devices lack traditional security measures like host-based firewalls, intrusion detection systems, or antivirus software, we need to be extra cautious. Basic sanitization of input helps prevent many common vulnerabilities, such as injection attacks or data corruption. Next, let's consider leveraging the permissions model used by the operating system. The permissions system on devices like iOS and Android is actually quite strong and provides a solid foundation for security. However, it's important to remember that external storage, like SD cards, may not always be as secure. So, we should be cautious when handling data stored outside the main device memory. Finally, always take advantage of the application isolation features provided by these systems. Both iOS and Android create a sandbox environment for each app, which helps contain potential security issues. Using this isolation effectively can significantly reduce risks and protect user data. By following these tips, validating input carefully, and leveraging the OS's security features, we can build more resilient and secure mobile applications. Let's talk about some practical tips for secure mobile application development. First up, using the least privilege model for system access is crucial. This means that your application should only request the permissions and access levels it truly needs to function. By doing this, you limit the potential damage if something goes wrong or if the app is compromised. You should carefully enumerate the services, permissions, files, and processes your app requires, and restrict it to only those. This way, the app isn't unnecessarily interacting with other parts of the device, which helps contain any security issues. Implementing the least privilege approach ensures that your app doesn't adversely affect other apps or system components, and it runs in the safest way possible. Next, let's discuss storing sensitive information properly. It's vital that you never store things like usernames, passwords, or other sensitive data in plain text on the device. Instead, always use native encryption schemes provided by the platform. Encryption adds that extra layer of security, making it much harder for anyone to access that information if they gain physical access to the device or if there's a security breach. Both of these strategies, limiting permissions and encrypting sensitive data, play a significant role in protecting your users, information, and maintaining the integrity of your app. They are essential parts of building a secure and trustworthy mobile application. Let's talk about one of the key tips for secure mobile application development: signing the application's code. Now, it's important to understand that signing the code doesn't inherently make the app more secure from a technical standpoint. Instead, it serves as a trust indicator for users, showing that the app has followed the necessary practices required by the device's application store. When an application is signed, it often gains certain privileges on the device, which can be crucial for its functionality. Conversely, unsigned applications tend to have more restricted access, fewer privileges, making them less capable of affecting the system or being exploited through various device channels. Depending on whether an app is signed and what type of certificate is used, the operating system grants different levels of privilege. So, signing your code is not just about compliance. It's about controlling how much access your app has and how it interacts with the device environment. In essence, signing helps ensure that your app is recognized as legitimate and can operate securely within the device's ecosystem, which aligns with the overall goal of developing secure, trustworthy mobile applications. Now, let's talk about some tips for secure mobile application development. First, it's crucial to figure out a secure and strong update process. Just like on desktops, if your application isn't fully patched, it becomes a major security risk, not only for your app, but also for the underlying operating system and the users themselves. So, you want an update process that's quick, easy, and doesn't consume a lot of bandwidth. This way, you can ensure that security patches are delivered efficiently and effectively. Next, let's consider the security strengths and limitations of mobile browsers. Unlike desktop browsers, mobile browsers have specific constraints. For example, cookies, cached pages, remember password checkboxes, and cached credentials all have limitations that can impact security. It's important to understand these differences because they affect how you handle data storage and authentication on mobile. And remember, do not treat the mobile browser as if it's just a smaller version of a desktop browser. Mobile browsers have unique behaviors and vulnerabilities. Recognizing these differences helps you design more secure applications tailored to mobile environments. By keeping these points in mind, you can greatly enhance the security posture of your mobile apps and protect your users more effectively. Let's talk about an important concept called zeroing out the non-threats. Now, even though threats to mobile devices and their applications are very real, not every threat is relevant to every app. It's crucial to understand which threats truly matter in your specific context. The best way to approach this is by first listing all the potential threats, what we call enumerating the threats. Then, you design mitigation strategies specifically around those real threats. For the ones that aren't relevant, you note them as accepted risks. This process is known as creating a threat model. Having a clear threat model helps developers understand all the possible risks to their system. More importantly, it guides them to focus their security efforts on the threats that pose the highest risk, instead of wasting resources on unlikely or irrelevant threats. Ultimately, this approach ensures that security measures are targeted and effective, making your application safer without overcomplicating the development process. This is a key part of building secure mobile applications, aligning well with the overall goal of proactive risk management. Let's take a closer look at the OWASP Mobile Threat Model. This model is a valuable framework that helps us understand the different security risks and vulnerabilities specific to mobile applications. It categorizes threats into various areas, such as data storage, communication, and reverse engineering, which allows us to systematically identify where our apps might be vulnerable. By understanding these categories, we can prioritize our security measures more effectively. The threat model also emphasizes the importance of considering both the client side and server side of mobile apps, since vulnerabilities can exist in either or both. Overall, the OWASP Mobile Threat Model serves as a comprehensive guide to help developers and security professionals safeguard mobile apps throughout their lifecycle. It aligns with our broader goal of building secure, trustworthy mobile experiences for users. Let's take a closer look at the OWASP Mobile Threat Model. This model provides a structured way to identify and understand the key security risks that mobile applications face. It helps us categorize threats based on the attack surface, which includes things like the data stored on the device, the communication channels, and the app's code. By understanding these categories, we can better anticipate where vulnerabilities might exist. What's really important here is that this model isn't just theoretical. It's a practical tool that guides developers and security professionals in designing more secure apps. It connects to our overall goal of building trustworthy mobile solutions by highlighting the areas where security measures are most needed. Essentially, it's about being proactive rather than reactive in safeguarding mobile environments. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. When developing secure mobile applications, one of the key tips is to use secure and intuitive mobile URLs. Many organizations actually rely on third parties to host their mobile sites, and often these sites will have domains that look quite different from the main organization's domain. This can sometimes cause confusion or reduce trust for users. It's common for companies to have mobile-optimized sites that are separate from their regular websites. While that's fine, it's crucial to keep the URLs intuitive and easy to recognize. For example, an intuitive URL might be icepartners.com, which clearly indicates it's the mobile version of the main site. On the other hand, less intuitive URLs like icepartners, mobi or icepartners, mobile vendor.com can be confusing or even look suspicious to users. So the takeaway here is, always aim for URLs that are straightforward and easy to remember. This not only improves user trust, but also aligns with security best practices by reducing phishing risks and making it clear that users are on a legitimate, secure site. This is a vital part of building secure mobile applications that users can trust and feel safe using. Let's take a closer look at the development and security aspects of the Apple iPhone. When developing for iPhone, security testing is a critical step to ensure that apps are robust and protect user data. It's important to understand the application format, which defines how apps are structured and distributed on the platform. Permissions and user controls are also key, giving users the ability to manage what data and features an app can access. Local data storage is another important point. Storing data securely on the device helps protect user privacy. Networking features enable apps to connect and communicate over the internet, but this also introduces security considerations. Additionally, push notifications, copy and paste functions, and other inter-process communication mechanisms need to be implemented carefully to prevent vulnerabilities. All of these elements, development, security testing, permissions, data storage, and communication, are interconnected. They form the foundation for building secure, user-friendly iPhone applications that respect user privacy and data security. Let's talk about how development is carried out. We use Xcode along with the iPhone SDK to build our applications. This setup allows us to run our code either within an emulator, which is great for testing across different scenarios, or directly on a physical device for real-world testing. Debugging is integrated right into Xcode, and we rely on GDB for that process, making it easier to identify and fix issues. Now, when it comes to the code itself, especially Objective-C, it's quite accessible. Standard OS X developer tools make decompiling fairly straightforward, which is an important point to consider from a security standpoint. It's crucial to understand that, unfortunately, preventing reverse engineering is quite difficult. Once the code is out there, determined individuals can analyze it. So, in essence, while development tools are powerful and flexible, they also highlight the importance of designing with security in mind, knowing that some level of reverse engineering is always a possibility. Let's talk about security testing in the context of Objective-C. While using high-level APIs like Objective-C can reduce the threat of classic C exploits, it doesn't completely eliminate them. It's important to remember that some vulnerabilities can still slip through. For example, to avoid buffer overflows, you should steer clear of manual memory management and instead rely on COCO objects such as NSString for string manipulation. However, even when using types like NSInteger, integer overflows can still occur, so caution is always necessary. Another critical issue is double-free vulnerabilities, where a segment of memory is freed more than once, leading to potential security risks. Most commercial static analysis tools aren't fully matured to detect Objective-C-specific flaws yet. But don't worry, simple free tools can still be quite effective for spotting issues with C API abuses. Connecting this back to our overall theme, secure coding practices and proper testing are essential to safeguard our applications from these kinds of vulnerabilities. Now, let's talk about how applications are actually built and distributed. Applications are compiled using Xcode, which leverages the GNU GCC compiler. This process cross-compiles the application for the ARM processor, which is what runs on the device, as well as for the local machine, which is used for testing with an emulator. Each application bundle that you create includes several important components. First, there's a unique ID, which helps identify the app. Then, there's a PLIST file containing entitlements and preferences. These define what the app is allowed to do and how it behaves. The bundle also includes a code signature, which is crucial for security and authenticity, any media assets the app needs, and of course, the executable itself. Now, when it comes to distributing iPhone applications, Apple has a pretty strict process. All apps must go through the App Store, where they need to be approved by Apple before they can be made available to users. This approval process is essential because Apple maintains control over the quality and security of the apps in their ecosystem. And of course, they reserve the right to revoke app distribution at any time if needed. Another key point is that all iPhone apps require signing with a valid code signing certificate. This process confirms that the app is from a trusted developer and is necessary to ensure security. To get this certificate, you need to be a member of the iPhone Developer Program. Now, on jailbroken iPhones, the rules are a bit different. Tools like Cydia and Installer are popular ways for users to install third-party software that hasn't been approved by Apple. This allows for more flexibility, but also poses security risks, which is why Apple maintains strict control over the official app distribution channels. So, in summary, understanding how applications are built, signed, and distributed is fundamental to appreciating the security and control Apple maintains over its ecosystem, while also recognizing the alternative methods used on jailbroken devices. Let's talk about permissions and user controls on Apple devices. Apple uses a security mechanism called Mandatory Access Control, or MAC, to restrict what applications can do. This helps ensure that apps operate within defined boundaries, enhancing security. The permission system on iPhone OS and OS X, often referred to as sandboxing, is based on the trusted BSD framework. This framework allows developers to create policy files that specify exactly what permissions an application needs, whether it's accessing the camera, location, or contacts. Each app is installed into its own directory, identified by a unique GUID. This setup means that apps can only have limited read access to certain system areas, and crucially, they can't read or write data in other apps' directories. This separation is key to maintaining privacy and security. By default, both the heap and stack areas in memory are non-executable, which prevents malicious code from running in those regions. More recent versions of iOS and macOS support address space layout randomization, or ASLR, which makes it even harder for attackers to predict memory locations, adding another layer of defense. Finally, when an app requests access to sensitive features like location or contacts, users are prompted with a pop-up at the moment of use. This gives users control over what information they share, aligning with the overall theme of user empowerment and security. Now, let's take a look at local data storage options on iOS. First up is SQLite storage. This is a very popular method for persisting application data because it allows for efficient storage and retrieval. However, it's important to remember that, like any SQL database, it can be vulnerable to injection attacks. To mitigate this risk, you should always use parameterized queries. This way, third-party SQL code isn't accidentally executed by your application, helping to keep your data secure. Next, we have keychain storage. The iPhone includes a built-in keychain mechanism borrowed from OS X, with some differences. It's designed specifically for storing sensitive data like credentials. The API for keychain is actually simpler than the Cocoa API, and it stores data as key value pairs in a dictionary. One thing to keep in mind is that keychain APIs only work on physical devices, not on simulators. Finally, there's shared keychain storage, introduced with iOS 3. This feature allows multiple applications to share data securely by defining additional entitlements. Developers need to explicitly specify these entitlements when setting up their apps, which adds a layer of control and security. Overall, understanding these storage options is crucial for managing data securely and effectively in your iOS applications. Let's talk about networking capabilities on iOS. First, the URL loading API. It supports common resource types like HTTP, HTTPS, FTP, and even local files, using APIs like NSURL connection and NSURL download. Keep in mind that when you make HTTP or HTTPS requests, the results are cached on the device by default, which can improve performance. Also, all cookies stored are accessible by any app that uses the URL loading system, so privacy considerations are important here. Next, we have NS streams. These are especially useful when you're dealing with network sockets for protocols outside of what the URL loading system handles. They give you more control over how connections behave, which can be critical for custom or more complex networking needs. Finally, there's peer-to-peer or P2P networking. iOS introduced this feature in version 3, allowing devices to connect directly via Bluetooth. This opens up opportunities for collaboration and data exchange without needing a traditional network connection. However, it also increases the risk of data theft, especially since both game and non-game apps can use it for sharing. Plus, since data can be streamed from an untrusted source, you need to be cautious and handle potential malicious inputs carefully. Overall, these networking tools are powerful, but come with security considerations that we need to keep in mind. Now, let's talk about push notifications, copy and paste, and other inter-process communication methods. Starting with push notifications, iOS 3 introduced this feature to allow applications to send notifications even when they're not actively running. This means your app can alert users with pop-ups or update badges on the app icon, keeping users engaged. However, it's important to remember that push notifications are not guaranteed to be delivered, so they should complement other forms of communication rather than replace them. Next, we have UI Pasteboard, which is similar to what you might know from OS X. This feature handles copying and pasting objects within an app, or even sharing data among different apps. When you copy something, the data is stored in item groupings with various representations. Think of it as supporting different formats, so the data can be used appropriately elsewhere. But, and this is crucial, any data shared via pasteboards should be considered untrusted. Since malicious data can be introduced, it's essential to sanitize the information before using it to prevent security issues. Overall, these features highlight how iOS provides flexible ways to communicate and share data, but they also require developers to implement security best practices to protect users. Now, let's take a closer look at the security architecture of the Google Android development platform. At its core, Android's security model is designed to protect both the system and user data through multiple layers of safeguards. One of the fundamental components is the permission system, which controls how apps access sensitive features and data. This ensures that apps only do what they are explicitly allowed to do. Another critical aspect is the securable IPC mechanisms, which facilitate communication between different processes while maintaining strict security boundaries. This helps prevent unauthorized data access or malicious interference. Application signing is also vital. By signing apps with trusted certificates, Android verifies the authenticity and integrity of applications before they run. Memory management security enhancements form an additional layer, safeguarding against attacks that target memory vulnerabilities. When it comes to files, preferences, and mass storage, Android implements security measures to restrict unauthorized access, ensuring that data remains protected whether stored locally or on external storage. Overall, these security features work together to create a robust environment where applications can operate safely, aligning with Android's goal of providing a secure and user-trusted platform for development and everyday use. Let's talk about the development tools available through the SDK. It offers free tools that make building and debugging your applications much easier. These tools support developers across different platforms, including Linux, Windows, and OS X, so no matter what system you're working on, you have what you need. One of the key features is the emulator, which simulates an ARM-based device. This means you can test your apps as if they're running on a real device, and it also supports various virtual hardware configurations. This flexibility is really useful for testing different scenarios without needing multiple physical devices. When it comes to debugging, the SDK has built-in support that works seamlessly whether you're using a physical device or the emulator. In fact, working with a device or the emulator is mostly interchangeable, making the development process smoother and more efficient. Most importantly, the code you develop using the SDK generally runs in the Dalvik virtual machine, which was the standard runtime environment for Android applications at the time. So, understanding how this VM works helps you write compatible and optimized code. Overall, these tools and features are designed to support you throughout the development cycle, ensuring you can create, test, and debug your apps effectively across various environments. Let's take a closer look at the platform security architecture. Android aims to be the most secure and user-friendly operating system for mobile devices. To do this, it reuses traditional security controls but tailors them specifically for mobile needs. First, it focuses on protecting user data, making sure your personal information stays private. It also safeguards system resources, including the network, to prevent unauthorized access. Another key aspect is application isolation, which ensures that each app operates in its own secure environment. This way, one app can't interfere with or access data from another. To support these goals, Android provides several critical security features. For example, the security at the OS level is robust, thanks to the Linux kernel underneath. It enforces strict controls and helps prevent malicious activity. Additionally, every application runs inside its own sandbox. This is the mandatory application sandbox, so no app can directly access another's data or resources without permission. Secure interprocess communication, or IPC, is also essential because it allows safe and controlled interactions between apps when necessary. Application signing is another cornerstone. Each app must be signed with a developer's key, which helps verify its authenticity. Finally, Android grants apps the ability to define permissions, which the user can grant or deny, giving users control over what data and features an app can access. Altogether, these features form a comprehensive security architecture that balances protection with usability, aligning with Android's overall goal of providing a secure and flexible mobile environment. Let's take a closer look at Android's security model. It's actually based on the Linux security framework, which provides a solid foundation. However, Android introduces some unique abstractions on top of that, tailored specifically for mobile devices. One key aspect is how Android uses Linux user accounts to isolate applications from each other, creating a sort of sandbox for each app. Now, permissions play a big role here. They're essentially rights that applications request to access certain device features, like taking pictures, using GPS, or making calls. When you install an app, it's assigned a unique user identifier, or UID, which helps protect its data from other apps. This UID acts like a digital ID card, ensuring that only authorized processes can access an app's data. The permission system is designed to minimize the risk of malicious software. Unless you explicitly grant an app powerful rights, like access to your camera or location, it can't do much harm. When you install an app or during runtime, Android's system keeps track of which permissions each app has. You might have granted some permissions when installing the app, or you may be prompted later to approve specific access requests. Overall, this permission and UID system is fundamental to Android's security, helping balance functionality with user control. It's a key part of how Android safeguards your privacy while allowing apps to perform their intended functions within safe boundaries. Now, let's talk about permissions, starting with permissions at the time of application install. Android uses what are called manifest permissions to keep track of what the user allows applications to do. For example, permissions to send SMS or access the camera. Before you install an app, you're shown a list of all the permissions it's requesting. This way, you can make an informed decision about whether you're comfortable granting those permissions. Once the app is installed, though, those permissions generally can't be changed. Now, moving on to the permissions of an already installed application. It's important to understand that these permissions are set at the time of installation and usually remain fixed. If an app needs new permissions later, you'll typically have to uninstall and reinstall it, or in some cases, update the app to request additional permissions. This system is designed to help protect your privacy and maintain control over what your device allows apps to do. So, always pay attention to those permission requests before installation, because they define what the app can access on your device. Let's take a closer look at permission protection levels. This slide highlights the different layers or levels of permissions that are put in place to safeguard sensitive information. These levels help us control who can access what and to what extent. At the most basic level, we have permissions that simply allow or deny access. But as we move up, the levels become more nuanced, allowing for more specific control over actions, like editing or sharing data. Understanding these levels is key because they align with the overall goal of protecting our data while still enabling productivity. It's about finding that balance, giving users enough access to do their work, but not so much that it becomes a security risk. By effectively managing these permission levels, we ensure that our information stays secure and that the right people have the right access at the right time. Let's take a closer look at some of the key mechanisms that help us communicate securely and efficiently in Android. First, activities are interactive screens that users engage with, and they rely on intents to specify which activity should be launched or interacted with. Intents are like messages that tell the system what action we want to perform. Next, broadcasts are a way for applications to send messages to each other across different parts of the system. When an app sends a broadcast, it packages the message into an intent, which can then be received by other apps or components interested in that specific message. Services are another important aspect. They run in the background, quietly performing tasks without direct user interaction. Think of them as the behind-the-scenes workers that keep things running smoothly. Content providers are a bit more specialized. They enable secure and efficient sharing of relational data between different processes. Since they're based on SQL, they allow for structured data management and access control, ensuring data privacy and integrity. Finally, the binder mechanism is central to all of this, providing a highly efficient way for different parts of the system, whether Java or native code, to communicate. It acts like a bridge, enabling seamless interaction across processes with minimal overhead. All these mechanisms together form a robust communication framework, supporting the overall stability, security, and efficiency of Android applications. Let's talk about applications signing on Android. Every application that runs on the platform must be signed by its developer. This signing process is crucial because if an app tries to install without being signed, it will be rejected either by Google Play or by the package installer on the device itself. The signed application certificate actually links the application to a specific user ID, which helps manage permissions and security. This is important because application signing ensures that one app can't access another app's data or features unless it's through clearly defined inter-process communication, or IPC. Developers have options when it comes to signing. They can use third-party certificates or self-signed certificates. Android makes it easy for developers to generate their own self-signed certificates, meaning they don't need external help or special permissions to sign their apps. Overall, signing is a key security measure that maintains the integrity of the app ecosystem and protects user data. It's a fundamental part of ensuring trust and safety in Android applications. Let's take a closer look at some of the key security enhancements in memory management that help protect systems from various vulnerabilities. First, we have ProPolice, which is designed to prevent stack buffer overruns. This is crucial because such overruns can allow attackers to execute malicious code by overwriting return addresses on the stack. Next, there's Safe IAP, which aims to reduce integer overflows, another common vulnerability that can lead to buffer overflows or privilege escalation. Moving on, extensions to OpenBSD's DLmalloc are implemented to prevent double-free vulnerabilities and chunk consolidation attacks. Double-free bugs can be exploited to cause arbitrary code execution, so these protections help mitigate such risks. OpenBSD also introduced a safer version of calloc to prevent integer overflows during memory allocation, ensuring that the requested memory size is accurately handled. Format string vulnerabilities are another serious concern, and protections are in place to guard against exploits that manipulate format strings for malicious purposes. On the hardware level, there's the No Execute, or NX, bit, a hardware-based feature that prevents code execution on the stack and heap, which are often targeted by attackers. In Linux systems, the mmap min-adder setting helps mitigate null pointer dereference privilege escalations by ensuring that certain low memory addresses are not accessible, reducing the risk of exploits. Lastly, address space layout randomization, or ASLR, is a technique that randomizes key memory locations, making it much harder for attackers to predict where specific code or data resides, thereby significantly increasing the difficulty of successful exploits. All these measures collectively strengthen memory security, which is vital in the broader context of defending our systems against evolving threats. Let's talk about files, preferences, and mass storage on Android. First, you'll notice that Android uses Unix-style file permissions. This means each application runs as its own user, so files created by one app are generally protected from access by other apps. Of course, users can allow access if needed, but by default, this setup enhances security. Next, there's shared preferences, a system feature that stores small pieces of data in a file with permissions similar to other files. This allows apps to save user settings or state information efficiently, while still maintaining control over access rights. Finally, Android devices often support larger add-on file systems mounted on memory cards. Since internal memory is limited, this expandable storage helps with space. But it's important to note that data stored on memory cards isn't protected. Any program on the device can access it, which raises security considerations. Understanding these storage mechanisms and permissions is key to appreciating how Android balances usability with security, especially as we manage different types of data across various storage options.